This is Mr. Craig, and this will be the third and last video for this example sheet, part 3, day 102. The first two examples already talked about example problem number 1 and example problem number 2, which are both first order reactants or reactions. Looking at the back side of this, we have example number 3, which states that we have a certain second order reaction, and again that's pretty important. Oops. Now let's get the pen working here. So, we have a certain second order reaction, and it says that it is 67% complete, and it has taken 27.3 seconds to consume 67% of this reactant. Question wants us to determine the rate constant and the half-life for this reaction. Alright, so first of all, recognizing that we have a second order reaction, we're going to use a different equation than the one that we've been using for first order. And this looks like this, where we have the inverse of the concentration at some point in time minus the inverse of the initial concentration. And that's all equal to K, which is positive, times our time. Now, the reason why we have a positive K here is, recall from earlier on in the discussion, that if I take the inverse of the concentration versus time, this is how I generate a positive, and that's a straight line I just drew there, a positive slope, which represents my K value. So the K will always represent the straight line, whether it's a negative or a positive slope in this case. Okay, so let me erase this. Okay. So that just is a little bit of a refresher and an easy way to remember which equation you wish to use on something like this. Alright, so we have our equation, and now we're ready to plug in our values here. So first of all, we need to determine the rate constant. So that means that we need to take our time and bring it down here. So now our equation will look like this, where the concentration at some point in time minus the initial concentration is equal to K, and then the time is below it. And again, that is a positive value. So what we want to do is figure out what our concentration is at some point in time. Well, that's what this is going to help us do. So if we've used up 67%, or 67% complete, how much of the reactant remains? Well, it should be around 33%, if I do my math right. So if we know we have 33%, and again, doesn't say what the molarity was, so go ahead and assume it to be a 1 mole solution. So I'm going to take 1 over 0.33, and I will subtract that from 1 divided by 1, because my initial concentration was 1 here, and then I will took 27.3 seconds to consume that amount, so I'll put my seconds down below here. And again, that should equal a positive value. Now, what's really cool, if you want to do some of that math in your head, if you take the inverse of 0.33, the 0.33 really is 1 over 1/3. Now again, if you take the inverse of the inverse, that equals 3. Okay, so and if you want to do this on the calculator, I am not opposed to that. Actually, it'll keep you out of a lot of trouble here. So, the inverse of 0.33 actually equals 3, minus 1 divided by 1 is 1, so 3 minus 1 is 2, and then divide that by your time, which is 27.3 seconds, and that will give me my K value. So let's do 2 divided by 27.3, and that gives a K value of 0.07, we'll say 33. Okay, and it really doesn't matter how far you go out. Just show at least 3 sig figs. On the AP exam, they're always going to be looking for something like that, and of course, always show your unit. So it'll be 1 over seconds, and for the most part, K will always be 1 over some time, which makes sense here. All right, so there's our K value, and again, that equals our K. So now we're ready to answer the next part, where it says the half-life. So again, using this equation here, if I'm using half-life, then that means I have half of my original concentration. So knowing that my K value is right here, I'm going to do 1 over, I'm going to scoot this down a little bit, 1 over 0.5 minus 1 over the amount that I started with. And again, I'm going to switch the t and the k here, since I now know what my constant is. And so I'm going to have over k, which is equal to my half-life time. So again, the inverse of 0.5 is just like saying that I have 1 over 1/2, which is equal to what? 2. So, and again, you don't have to do it that way, but if you need to. So I'm going to have 2 minus 1 over the k value, which is 0.733. And again, the unit's 1 over seconds, so put seconds in the correct spot. So whatever 2 minus 1, which is the inverse of my k value, so you have that in your calculator, hit the inverse button, and it says it's 13.65 seconds. I'm going to make that 13.7 seconds for 3 sig figs. And then you need to ask yourself, does that answer seem logical? Well, coming back up here, for 67% of the reaction to be complete, it took 27.3 seconds. So my answer should be less than 27, and it is. It's 13.7 seconds. So yeah, that seems like a very good answer. I hope these 3 videos have really helped you on understanding how to do first and second order reactant problems with these equations that involve natural logs. If you see, or if a kinetics question is asked on the AP exam, I guarantee you will see something that looks just like one of these 3 problems. And as always, I hope these videos have helped.